Imagine a world where quantum computers solve problems so complex that even the most powerful classical supercomputers fall short. Tech giants like Google, IBM, and innovative startups such as Photonic Inc. are in a heated race to bring fault-tolerant quantum systems to fruition. These systems promise to revolutionize fields ranging from cryptography to materials science. Artificial intelligence and quantum computing are two of the most transformative technologies of our time. While they are developing along distinct paths, their convergence is inevitable and will likely redefine the technological landscape. At the heart of quantum computing lies the qubit, the quantum equivalent of a classical bit. Unlike a classical bit, which exists as either a 0 or a 1, a qubit can be in a superposition of both states simultaneously. This property is represented mathematically by probability amplitudes, complex numbers that dictate the likelihood of the qubit being in either state. The sum of the squares of these amplitudes always equals 1, ensuring the probabilities are normalized. One of the biggest challenges in quantum computing is maintaining the delicate quantum state of qubits. Qubits are highly susceptible to decoherence, a process that disrupts their quantum properties, such as superposition and entanglement, often triggered simply by the act of measurement. Environmental interactions can also cause decoherence, introducing errors that can propagate through quantum gates and compromise the accuracy of computations. There are two primary types of errors that can occur in qubits: bit flip errors, where a qubit switches from 0 to 1 or vice versa, and phase flip errors, which alter the phase of a qubit without changing its amplitude. Since quantum states are described by both amplitude and phase flip errors specifically impact the latter. To tackle these issues, quantum error correction, QEC, codes have been developed. These codes distribute quantum information across multiple physical qubits, creating a single logical qubit whose state can be monitored and corrected to maintain computational accuracy. One popular approach is the surface code, which arranges qubits in a 2D grid, using measurement qubits, also known as ancillas, to detect errors through stabilizers, operators that monitor the parity of qubits without collapsing their quantum states. For instance, consider a system with 4 data qubits. An ancilla qubit can determine if the number of bit flip errors is odd or even by checking the parity. If the result is 1, there are no errors or an even number of bit flips. If the result is -1, there is an odd number of bit flips, indicating the need for correction. Despite their effectiveness, surface codes require an impractically high number of physical qubits for each logical qubit, limiting their scalability. Quantum low-density parity check (QLDPC) codes offer a more efficient alternative by reducing the number of parity checks each qubit participates in, thereby decreasing the overall resource requirement. QLDPC codes can use up to 10 times fewer physical qubits per logical qubit compared to surface codes, making them better suited for large-scale quantum computing. Photonic Inc. has made significant strides in this area by developing a new family of QLDPC codes called SHYPS codes. These codes are designed with efficient logical computation in mind, overcoming the previous challenge of implementing complex logic in a single time step. SHYPS codes enable the execution of algorithms with depths and runtimes competitive with those of surface codes, but with a much lower physical overhead. Photonic's platform leverages the spin of electrons or nuclei in silicon to store quantum information, offering long coherence times and high fidelity. Photons are used to transmit information between qubits through optical waveguides, facilitating both local and remote communication. Each T-center, a defect in silicon, formed by replacing a silicon atom with 2 carbon atoms and a hydrogen atom, serves as both a memory unit and a computational element, enabling entanglement operations. By integrating thousands of T-centers into a 2D grid, Photonic can create scalable quantum processors. This modular architecture supports efficient error correction using QLDPC codes, minimizing the overhead required for error detection and correction. Stephanie Beal, Senior Quantum Technology Liaison at Photonic, discussed the company's advancements in quantum error correction with embedded. She noted that Photonic's SHYPS codes could significantly accelerate the timeline for practical quantum computers, particularly for high connectivity architectures. These codes require 5 to 20 times fewer physical qubits per logical qubit compared to surface codes, reducing the hardware requirements for implementing commercially relevant quantum applications. When asked about the availability of fault-tolerant quantum machines, Beal expressed optimism. While exact timelines vary, she emphasized that recent advancements across various aspects of quantum computing have undoubtedly moved the field forward. Photonic's entanglement-first platform, which enables high connectivity and flexibility, plays a crucial role in this progress. In conclusion, the development of efficient quantum error correction codes like SHYPS is a critical step towards realizing practical quantum computers. As Photonic continues to innovate, we can look forward to a future where quantum computing becomes a reality, transforming industries and solving problems previously deemed unsolvable.